Straightening an iron rod after bending it is not an easy task. It takes a lot of time and energy to straighten. Even then, it's not entirely straightforward. We observe such things not only in iron but in every metal. But if you are told there is a material that can remember its initial shape, no matter how much the metal is twisted or enlarged, a small amount of heat will cause it to return to its original shape. As strange as it may sound, there is a material with unique and amazing properties called nitinol. Nitinol can remember its initial shape, so it is called a shape memory alloy. Another property of nitinol is superelasticity. Nitinol's unique qualities make it useful in a variety of space missions as well as medical equipment. And with nitinol becoming popular day by day, don't be surprised if you see nitinol instead of tires in cars in the future. The discovery of this amazing nitinol was almost as coincidental as the discovery of aerogel. William J. Boiler accidentally discovered nitinol in 1959 while developing complex missile materials. Nitinol is an alloy made from a combination of nickel and titanium, which is 55% nickel and 45% titanium. No matter how much you bend or twist nitinol in hot water, it will return to its original shape. If you take a nitinol wire to your desired shape and heat it to 500 degrees Celsius, the nitinol will remember the previous shape. But why other materials other than nitinol do not have such properties? The main reason for the unique properties of nitinol is the phase transmission. We are all familiar with phase transmission. For example, there are three types of phase of water. The solid phase of water is ice. When ice is heated, the phase of water changes and becomes liquid. If liquid water is heated more, the water turns into steam. These are the three phases of water: solid, liquid, and gas, and phase transmission from one phase to another occurs as a result of temperature changes. Notice here that we are seeing the same water in three different forms, and which form we see depends on how the water molecules in the water are arranged. In liquid water, water molecules hold together gently. On the other hand, the molecules of solid water, i.e. ice water, are very close together. You will be surprised that solid water has several phases. For example, the hexagonal ice phase is stable between 32 degree Fahrenheit and minus 150 degree Fahrenheit. Cubic ice phase, which is stable from 150 degrees Fahrenheit to minus 330 degrees Fahrenheit. We do not normally see these phases of ice because normal conditions do not have such low temperatures. Like ice, nitinol has different phases in its solid state. One of these is the low temperature phase called martensite. When the temperature increases, a high temperature phase called austenite appears. Now, if nitinol is placed in any form and heated to 500 degrees Celsius, the molecules of nitinol become high temperature phases or austenite phases. Later, when cooled in cold water, it turns into martensite. Then no matter how much you twist the nitinol in that state, the molecules will remain in the martensite phase. Only the structure of the molecules will change, even though the phase will not change. But whenever you heat it or put it in hot water, the nitinol phase will change to austenite phase. That is, the austenite phase will return to the size that the nitinol had. This is basically how nitinol's shape memory works. The unique property of nitinol compared to other metals is that it retains its shape after deformation without breaking any bonds when oxidized. Such as copper is oxidized, the bonds between them are broken, but nitinol does not break any bonds, so nitinol can easily return to its original form. Another characteristic of nitinol is superelasticity. When any material is bent or deformed to a certain extent, it returns to its original state, which is called elasticity. All objects around us are more or less elastic. Copper shows little elasticity. Copper does not return to its original position when bent slightly, but nitinol is superelastic. If you twist the nitinol completely, it will go back to its original shape. Phase transmission is also responsible for this superelasticity property in nitinol. The austenite phase is set at room temperature, i.e. 20 to 25 degrees Celsius, to impart superelasticity properties to nitinol. As a result, nitinol is deformed to the martensite phase and then it goes to the austenite phase even if no temperature is applied separately. As a result, nitinol is deformed to the martensite phase and then it goes to the austenite phase, even if no temperature is applied separately, because the temperature set for the austenite phase is 20 to 25 degrees Celsius. As a result, nitinol reverts to its original form without the application of heat. And through this, nitinol superelasticity is obtained. Nitinol is used in some high-end eyeglass frames due to its superelasticity. No matter how much these glasses are bent, the frames will automatically return to their original position. It is a power generator made of perhaps the simplest mechanism in the world. Here is the nitinol between the two wheels. Now, if the lower wheel is placed in hot water and the wheel is rotated a little, it will rotate because the hot water at the bottom forces the nitinol to go into its original shape, causing this rotation. This mechanism offers opportunities to generate electricity from many readily available sources. For example, sunlight that hits water can turn turbines to generate electricity. Also, the temperature difference between the top and bottom of the seawater can be used. Moreover, many of us are familiar with the issue of wearing heart rings for heart problems. The ring used here is also made of nitinol. Here, austenite phase is active at 37 degrees Celsius. As a result, the nitinol ring, when placed in the blocked blood vessel, expands to the austenite phase at 37 degrees Celsius and normalizes blood flow. Moreover, in this condition, it exhibits superelasticity properties, as a result of which nitinol does not change its shape no matter how much it is twisted. Because nitinol can remember its shape at high temperatures, it is not surprising that it will modify itself like a remote control for any metal without any electrical instructions, and this technology will be used in various fields. When sending a robot to another planet, various factors must be considered. For example, the robot's weight should be kept as low as possible, and the materials used should be fit for survival in the environments of various planets. 3 rovers sent out to Mars, Sojourner, Curiosity, and Opportunity used aluminum wheels. Although 2 of these robots performed well, the Curiosity rover's wheels are severely damaged due to its weight of almost 1 ton. Naturally, thin aluminum wheels can't carry such a huge amount of weight. So from now on, NASA is interested in using something else instead of aluminum for any future missions. Nitinol can be best choice in this case, as nitinol is light in weight as well, and its superelasticity make it suitable for any road. NASA is already working with nitinol. They have made wheels with nitinol and are testing these wheels in various adverse environments. Perhaps future missions to Mars may see the use of nitinol wheels. It can be used in the cars we use in our daily activities in the future. However, we may have to wait a long time to see results because nitinol is now highly expensive. Moreover, it needs more technical improvements. However, you can purchase nitinol from Amazon if you prefer. A decent quality nitinol for science project should cost you $15 to $20 on Amazon. Have you ever had the feeling that you might be living in the past, or that the present is just an illusion and what we see in real life is not real? If so, you may be interested in watching this video to learn more about this strange reality of nature. And if you like the video, you can subscribe to our channel.